We can't talk about proof without, of course, looking at induction, which we saw in extension 1. A reminder of what we saw in extension 1. We had the series type of questions. Let's look at this one. I've written it in some notation. I want to prove that particular thing. So the idea was, first of all, let's prove it true for the first case. Sometimes people call it the base case. R equals 1. Now here's the first key difference. R equals 1, yes, that's what we did do in extension 1. But of course in extension 2 now, it doesn't necessarily have to start at 1. This one does. Okay, left-hand side, if I substitute into that general term, I get 2/3. Right-hand side, substitute into that one, and again, I get 2/3. So yes, it does work for n equals 1. We now basically assume what it is that we're trying to prove. So n equals k, where k is some positive integer. I'm leaving it in some notation. So it's now going 1 to k of that expression. I now want to prove it true for the next case, that k plus 1. So now my sum would go from 1 to k plus 1. And just a quick note here, on the left-hand side, if we're leaving it in some notation, the general term doesn't change. So I'm still substituting into 4 on r plus 1, r plus 2. What's changing is the upper limit. That's k plus, and on the right-hand side, sure, that changes. So we get 1 minus 2 on k plus 2, k plus 3. Okay, our proof. Well, for our series type, so I pull the last case, when it's k plus 1, out of the sum notation. That leaves me with the sum, which was my assumption over there. So let's sub that assumption in, and now we have algebraic fractions to play with. I'm not going to do anything with the 1. It doesn't make sense because my answer has 1 in it. So I'll leave that. But I'll combine the other two fractions together. Common denominator, k plus 1, k plus 2, k plus 3. Again, I've got to watch out here because it's minus this fraction. Now, when I've set up my fraction, I've left the minus out the front because, of course, what I'm trying to prove has minus out the front as well. So I've pulled out a negative factor, hence why it's negative 4, but it'll be plus the 2 lots of k plus 3. Let's play around with the top of the fraction, and now I can get it to a point where the k plus 1's factorise, and that was what we had to prove. Now remember, that part of the induction is basically a direct proof, a deductive proof. So we conclude it with our if-then statement, what we've just done. I've not written it specifically as if-then. I suppose I could have said, hence, if it's true for n equals k, then it's true for k plus 1, and actually write it as an if-then statement, but it's basically saying the same thing. Now, hence the result is true for n equals k plus 1 if it's true for k. That now allows me to induce the whole solution. I combine that first step with the second step, and so since I know it's true for n equals 1, then I know it's now going to be true for every integer. And again, I mentioned which method I've used. Well, by induction, I've induced the solution. Now here's one, well, it's quite old now, slightly different. Instead of being a sum of terms, it was the multiplication of all terms. But here you'll notice the first case is 3, not 1. So you've got to be careful with that. But other than that, the actual technique's the same. Remember, induction is just a technique of proof. It's an idea. That doesn't change. So prove it true for n equals 3. I'll get 1/3 on the right-hand side. Yep, I get 1/3 as well. So yes, it is true for that first case when n equals 3. I'm going to assume it's true, but this time it's not just integers, it's integers such that they're bigger than or equal to, in this case, 3. There's my assumption. I want to prove true for the next case. I'm just highlighting it by adding in the second last term in the pattern to say, hey, all of that, of course, is my assumption, and then I'm multiplying it by that last term. Now, let's play around with this one. Get a common denominator over here in the parentheses, which would just be k plus 1. Now, multiplying these together, we'll get, there we go, 2 on k plus 1, that was what we were trying to prove. So that one drops out quite nicely. Hence it's true for k plus 1. If it's true for k, since it's true for n equals 3, then it's true for all integers bigger than or equal to 3 by induction. Be very careful with something like this because it's easy to fall into habits. And by habit we go, oh, since it's true for n equals 1, da 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 da. Well, of course, it's not n equals 1 in this case. So the other type of one we looked at in extension 1 was the divisibility types. I'm going to prove n squared plus 2n is a multiple of 8, but now the n is going to be an even number. Yeah, that's slightly different to what we see in extension 1. It's going to be an even number. That means my first case will now be n equals 2, the first even number. 2 squared plus 2 times 2 is 8. That is divisible by 8. So yes, it's true for n equals 2. Assume it's true for n equals k, but again now I've got this condition on k. K is an even number. In other words, my assumption is that k squared plus 2k is equal to 8 times something, where that thing is an integer, but I'm also assuming k is an even number. And that becomes important in my proof. The next case now would not be k plus 1, because I'm dealing with even numbers. So the next case is k plus 2. That is what I'm trying to prove. K plus 2 squared plus 2 outside of k plus 2 is 8 times something, and again that has to be an integer. How do I get my assumption in there? I've got to get basically k squared plus 2k in there somehow. So I do have them. Look, I've got the k squared there and the 2k there. So I've got 8p and I'm left with 4k plus 8. I want to show this is divisible by 8, so I pull it out. I've got a problem here, k divided by 2, and that's why the assumption that k is an even number becomes important, because it means k divided by 2 is an integer. Okay? If I just assumed k was an integer, well, that'd be no good. I might have a half or 3 on 2. Where q is equal to that, it is an integer, but again I'll highlight why I know it is, because I know k is even. Hence it's true for k plus 2 if it's true for n equals k, and since it's true for 2, then it's true for all even numbers. Of course, another way you could approach that, I'll just jump straight to the assumption. Instead of assuming k is an even number, I could still use positive integers, but instead define n to be 2k. And that forces n to be an even number. So it's still then 4k squared plus 4k is 8p, but now prove true for the next one, well the next even number would be 2k plus 2. And so that's what I now want to prove. And let's prove that one. Expand that out. Again, here we go. I've got the 4k squared and I've got the 4k there. That becomes 8p, but this time 8 comes out very nicely as a factor. It doesn't really matter which way you go, but okay. Now that brings us to ones that we don't see in extension 1. Inequalities. Of course, now we've been looking at inequalities as well. We can have it inside an induction problem. I'm going to prove that 2 to the power of n is greater than n squared. The first case then would be n equals 5, because it's integers greater than 4. Left hand side of this one is 32. Right hand side is 25, and yep, 32 is bigger than 25. Hence it's true for n equals 5. I'm now going to assume true for n equals k. K is an integer, but k is greater than 4. Again, this will become a key part of my proof. In other words, 2 to the power of k is greater than k squared, and also k is greater than 4. We want to prove it true for the next case, k plus 1. 2 to the power of k plus 1 minus k plus 1 squared is greater than 0. So what I'm going to do is I'm going to try and prove that idea with inequalities. Hey, let's move everything to one side and just try and show it's always positive. So that's what I'm going to try and prove. I've got to get that assumption in there somehow. The assumption involved 2k, so 2 to the power of k. Well, I could rewrite that first term of 2 to the power of k plus 1 as 2 times 2 to the power of k. This allows me to get the assumption in. But that now means that it's greater than rather than equal to, because our assumption was 2 to the power of k was greater than. That becomes k squared minus 2k minus 1. I'm going to factorise this. Well, basically I'm completing the square. That becomes k minus 1 squared minus 2. Remember, I'm trying to show this is always a positive number. Oh, hang on. Well, k minus 1 squared, that's certainly positive. But if I subtract 2, but hang on. I can now say that's greater than 3 squared minus 2, because using the other part of my assumption, we said k was greater than 4. So that's okay. Now, here's where you've got to be careful in your proof. It is tempting to just substitute 4 into that third line. You would still come up with the answer. However, it's not valid. right? Because you've got to preserve the inequality. Remember, in order to add inequalities together, the inequality signs need to be in the same direction. So whilst if I substitute in k is greater than 4, yes, k squared would be greater than 16. You can't say negative 2k is greater than something. It would be negative 2k is less than minus 8, because if k is greater than 4, you change the sign, and now the inequality signs are not running in the same direction. So I need to get it to the point where when I substitute in, everything I substitute into, that inequality is running in the same direction, which is why I need to do it this way. So then I highlight yes. And we get the answer 7, and 7 is a greater than 0. Yep. It's true for k plus 1 if it's also true for k. Since it's true for n equals 5, then I know it's going to be true for all integers greater than 4. Let's try this one. Or 1 plus 1 on 2 squared plus 1 on 3 squared and so on is always going to be less than or equal to 2 minus 1 on n. First case. Left hand side is just 1. The right hand side is 1 as well. That's okay, because remember we're trying to show it's less than or equal to. Well, it's equal to. So it satisfies that. Hence it's true for n equals 1. Assume it's true for k. Now, in other words, I'm going to assume that one. In this case, the only condition on it is k being a positive integer. Prove it true for the next case. Again, playing with inequality, I'm going to pull everything to the left-hand side and attempt to show that this expression is always negative or equal to 0. Let's get our assumption in there. There we go. So this is going to be less than or equal to that expression. Well, that's nice. 2 minus 2, that disappears. Make it all one fraction, k plus 1 squared on the bottom. Let's play around with the top. I get negative 1 on the top. Let's look at what we've now got. Well, I'm trying to show it's always less than or equal to 0. Well, negative 1, that's certainly always less than 0. K plus 1 squared, well, that's always going to be positive. K we've assumed is a positive integer, so that's going to be positive. I've got a negative divided by a positive. Well, that's always going to be negative. So, yep, I can say that's always less than 0. It's not actually true to say it's less than or equal to 0, because I've got a fraction with a constant on top. So I've just written less than 0, but if it's less than 0, it's then okay to say it's less than or equal to 0. And hence the result is true for k plus 1 if it's also true for k. Now, the actual induction idea. Induction is just a method of proof. Here's one we're going to do which is a little bit different. So with 2 vertical walls and a floor meet in a corner, a cube is placed in the corner. A solid shape is then formed by placing identical cubes to form horizontal and vertical stacks, rows and what have you. There's an example which uses 9 cubes. So n is going to be the number of cubes used to make the solid. We're going to show that the number of exposed faces of the cubes is always going to be 2n plus 1. Well, the idea would be prove it true for n equals 1. Well, what is n equals 1? Well, it's when we've got one cube sitting there. And don't be afraid to draw diagrams to explain your proof. So there we go. I've got a cube. I can see I've got 3 exposed faces. Well, the formula said n equals 1, so 2n plus 1. Yes, that is 3. The formula works for when we have one cube. Hence the result's true for 1. We're now going to assume it's true for n equals k. In other words, I'm going to assume that k cubes will have 2k plus 1 exposed faces. We now want to prove that k plus 1 cubes will have 2k plus 3 exposed faces. Now, here's my proof, but I'm going to use a diagram. You see, if I add a cube to a picture, so the addition of a new cube, if I put a new cube somewhere, what it'll do is it'll end up covering one existing face. I can see that. Alright, so I put it there, bang, I've covered up one face. However, I've also now created another 1, 2, 3 faces when I do that. Now, it doesn't matter where I put the cube, that's always going to happen. So what I now know is the number of exposed faces of k plus 1 cubes will be what I had originally, but then I've subtracted one face, but added another 3. Well, I assumed that k cubes had 2k plus 1. Subtract 1, add 3, I get 2k plus 3. And that was what I wanted to prove. Hence the result's true for k plus 1 if it's true for k, etc., etc. So don't be afraid to draw diagrams in your proof. As long as it's clear and you explain it well, it can be a good proof. The next type of induction problems involve recursive formulas. Remember, they were the ones where we could write our series in terms of previous terms and things like that. Now, if your recursive formula is defined in terms of m preceding terms, because it might not just be one term, it might be a combination of several terms before, then we're going to need to prove it true for the first m terms. And we're also going to have to make an appropriate number of assumptions, because if you think about how we will finish off, say you were involving something that was involving the previous two terms, then I'd have to prove it true for the first two terms. So that in my conclusion I can say, oh well, since it's true for the first two terms, now it's going to be true for the third term because it involved that. But by the way, classic mistake people sometimes make is they try and prove the recursive formula. No, that's a given piece of information. It's a fact you're allowed to use. We're saying this. Okay, so here's a quick little one. Sequence is defined by, the first term is the square root of 2, and every subsequent term after that will be the square root of 2 plus the previous term. We have to prove that every single term of this pattern will be less than 2. Prove it true for the first one, which they told me is the square root of 2. And the square root of 2 is, of course, less than 2. Hence, it is true for that first term. Assume it's true for k. So I'm going to assume, sure, the kth term is less than 2. And now I want to prove that the k plus 1th term is less than 2 as well. So I'll start with that recursive formula. That's how I'm going to get the assumption in there. Because I've been told that the k plus 1th term is the square root of 2 plus the previous term, which I've assumed is less than 2. Therefore this must be less than the square root of 2 plus 2. 2 plus 2 is 4, square root of 4 is 2. So yes, the next term is less than 2 as well. True for k plus 1 if it's true for k, hence it's true for all positive integers. Okay. Fibonacci numbers are fun, but this pattern requires the previous two terms. If you remember Fibonacci, you add the two numbers before. So there's the formula, an plus 1 is an plus an minus 1. So you add together the two previous terms, and the first and the second term are both equal to 1 in a classic Fibonacci sequence. We're going to prove that every term is less than 1 plus the square root of 5 on 2 to the power of n. And the significance of that number, that's phi. That's the irrational number phi. Okay, so I'll prove it true for those first two terms. So n equals 1. First term is 1. 1 plus root 5 on 2, that golden ratio, power of 1, 1.6, well, 2, and it goes on and on. But it's certainly less than 2. So that's okay. What about the second term? Second term is also 1, but that squared becomes 2.62. Yes, 1 is less than 2.62, so it works for the second one as well. So, yep, it works for those first two. I'm now going to assume it's true then for both k and k plus 1, so two consecutive terms there. Now, in other words, I'm assuming both of these things. I'm now going to prove it's true for the next case. So in other words, again, I'll use the idea of let's pull everything to one side. I'm going to show this is negative. ak plus 2 minus that, I can use my recursive formula. It becomes ak plus 1, but we said ak was less than 1 plus root 5 on 2 to the power of k, so I can substitute that in, and k plus 1, 1 plus root 5 on 2 to the power of k plus 1. I've got to prove this is negative. Well, there's a common factor there, so I may as well pull that out. And of course, that's a positive number. 1 plus root 5 on 2 to the power of anything's going to be positive. So really, I now want to show what's in these brackets is negative. Let's play around with that. Make it all one fraction. I've got 4 on the bottom. Well, that's positive. So now it's the top of the fraction. Expanding out, actually it turns out to be 0. It's less than 0 there. Because if you read down your inequality, we had already said it was less than that expression here. And so we're saying it's less than something that's equal to 0. All right. I've got the expression that I want. So yep, it's true for k plus 2 if it was true for k and k plus 1. But hey, we know it's true for 1 and 2, so it's got to be true for all of them by induction. Let's have a look at an HSC one. 2022. also involved the square root of 2. So A1 is the square root of 2, A2 is the square root of 2 plus the square root of 2, A3 is the square root of 2 plus the square root of 2 plus the square root of 2, so it's all nested together. So in other words, here's the pattern, here's the formula. An plus 1 squared is equal to 2 plus the previous term. And somehow we get trig into this. Use mathematical induction to prove that every term is actually equal to 2 times the cosine of pi on 2 to the power of n plus 1. Okay, that's what we're trying to prove. First case then, n equals 1. First case, 2 times the cosine of pi on 2 squared, which is pi on 4. Cos of pi on 4, one of our exact values, is 1 on root 2. 2 times 1 on root 2 is root 2. Yep, works for n equals 1. I'll now assume it's true for k. I want to prove it's true for k plus 1. There's the recursive formula. K plus 1 squared was 2 plus k. We assumed that term k was 2 cos pi on 2k plus 1. I now have to play with this. Okay, so yep, that was my assumption I've just used. I'm going to rewrite this in an interesting way. 2, there's a common factor of 2 there. But rather than pulling out a common factor of 2, I put out a common factor of 4 and a common factor of a half. Weird. Why? Because now I'm going to say, hang on, the cos of pi on 2k plus 1 is the same as saying 2 times pi on 2k plus 2. And look what I've got. A half of 1 plus cos 2 theta. That's a trig result that we know. I can replace that with cos squared theta. Theta being pi on 2 to the power of k plus 2. Well, that's what term k plus 1 squared is. Therefore, term k plus 1 is 2 cos pi on 2 to the power of k plus 2. Hence it's true for k plus 1 if it's also true for k. And since it's true for 1, we know it's true for all of them. That was a nice little one. Certainly different to what we see in extension 1. So we'll spend what's left of today and tomorrow working on some induction problems.